So let's simplify just as extra practice. Oh, hang on one second. Let me turn on the light on this thing. All right, it might help a little bit. All right, let's simplify the cube. So that's a 3 cube root. It's a little 3 of 48 x to the 6th, y to the 7th, z to the 8th. Let's see what that looks like. So we're going to simplify that just for extra practice. Oh, excuse me, for extra practice. Okay. Give me 1 second. You can start working on it if you'd like. Need to check something. All right. And remember, you can raise your hand or just speak up or use the chat if you have a question. Okay, so let's simplify the cube root of 48 times x to the 6th, y to the 7th, z to the 8th. So we already know the rules for radicals tell us that we can split this up into 4 different radicals, right? Because there's a product, there's the 48 times this x term, y term, z term. And in fact, if you want, if you like to work this way, you can split them up and literally like write them out individually and work them individually and then just put all the pieces back together. Maybe, maybe you like doing that. Okay. So the first thing to do with the numbers, so the numbers are trickier because you need to find a perfect cube factor that goes into 48, meaning that factor is 48. So we need a perfect cube factor that divides 48. I'll just say goes into, because that's like the colloquial kind of way to say it, that goes into 48. And what are those perfect cubes, by the way? Remember, they're one is always going to be in the list, but it's not really that useful, right? 1, 8, 27, 6, so 2 cubed, 3 cubed, 4 cubed, 5 cubed, etc. Obviously, we're not going to be dealing with 64 can't go into 48. Neither can 27, right? If you think about it, you can check that and make sure. But in fact, 8 does. So what I'll do is I'll write 48 is 8 times 6 under the radical, split it apart, cube root of 8, times cube root of 6. And the cube root of 8, I've picked it for a reason, right? It factors, or rather, cube root of 8 simplifies into a nice whole number, 2, and then I'll just tack on that cube root of 6. And cube root of 6 does not have any perfect cube factors, so I'm done. Or rather, I'm done with the 48 at least. So that's how we deal with those numbers. Now, what about a variable with an exponent? Now, we can... Oh, I'm sorry. God, I don't know what happened to me right before lecture started. Just sneezed like 10 times in a row. All right, so we can write this in rational exponent form. And if we, so there's multiple ways to do this, right? There's the way of saying how many times can 3 go into 6, right? That's like the most intuitive way. And if you get a nice whole number answer to that, like 2, right? How many times does 3 go into 6? 2 times, then that's your exponent. And there's really nothing else to say. But do recall that you can also, so alternatively, you can write it in the form x raised to the 6 over 3, right? Using our rational exponent rule. And that, of course, it's still going to give you the same answer, right? 6 over 3 is still 2. Okay. Now, what about the y to the 7th? Cube root of y to the 7th. So I'm just moving through these terms. Cube root of y to the 7th. How many times can 3 go into 7? Well, still twice, but it's not exactly the same as this because there's an extra piece left over. So if I ask you the question, how many times can 3 go into 7? What you should say is 2 times with 1 left over. So let's interpret that. So when I say how many times can 3 go into 7? The answer, of course, is twice, I'll say 2 times with 1 left over. How do we interpret that? Oh, gosh, okay, with 1 left over. That's going to look like this. The 2 times, the 2 whole times that 3 goes into 7, that comes on the outside, and then that's the exponent on the y. The 1 left over is the y that gets left under the radical with an exponent of 1. So there's the 2 times. So how many times does 3 go into 7? Twice, with 1 left over. Left over meaning left in the radical. And again, we could write this in rational exponent form. Y is 7 over 3, if you like that way better. And write 7 over 3 as a mixed number. If you recall how to do that, write it as a mixed number, then it's 2 1/3, right? But y to the 2 1/3 is 2 whole y's with 1 left over out of 3 with a third left over. But that's just the same as, remember, y to the 1/3 is just the cube root of y to the first. So they get you to the same place. It just depends on what you like better. You know, most of you are probably going to like the first way I did it because it's a little bit more intuitive. The second way is a little bit more formulaic, I guess, or there's more of an operation to it. All right, the last term is z to the 8th under the cube root. Okay, last term is z to the 8th under the cube root. Let's do it this way. How many times can 3 go into 8? That's twice again, right? With 2 left over. This time there are 2 left over, so there's 2 z's left over under the radical. And now to put everything together, I'll put all the numbers that and letters that are on the outside of the radical together. So from the 48, well, first let me write the whole problem again. From the 48, we had a 2 on the outside. From the x to the 6, we had that x squared coming outside. We had a y squared on the outside, and we had a z squared on the outside. That's all the stuff that came out of the radical, squished together there. Now here comes the rest of the radical. We had a 6 left under there. We had no x's left under there. We had a single y, and we had a z squared left under. Okay. Okay, so that is our radical slash rational exponent problem for today, which it took 10 minutes to do because sometimes these problems can be pretty involved, but once you do them enough, you get to this point where you're just asking this question over and over. Now the number, the 48, you know, factoring that can be a little tricky sometimes depending on what the number is. But then you'll find with the variables, with the variables, you really are just asking this question, how many times can blank go into blank, just over and over. And as long as you are good with that kind of question and interpreting the answer, then the variables should get pretty quick for simplifying radicals with variables under them. All right, I'm going to move on now to section 0.6, or in the book it's called, in the homework on WebAssign it's called 0.6, in the text they call it P, section P6 for prerequisite. I'll call it 0.6. All right, let's get through as much of this as we can, maybe even finishing it today and moving into 1.1. All right, factoring rules. We're going to go through them quick. Well, first of all, defining factoring. Factoring is writing it, let's see, as an expression, writing something. It could be a number or a polynomial. I'll just be vague and just say something as a product. I mean, that's literally like I don't need to be too technical about it. Factoring something is just writing it as a product. So for instance, I can write 48 as 8 times 6. I'm writing something as a product. Remember, a product is a multiplication problem. Or I can write x squared minus 4 as x plus 4 times x minus, or sorry, no, that's not it. I can write x squared minus 4 as x plus 2 times x minus 2. If you recall the difference of squares, which we'll talk about in a little bit more detail, but that's just a quick example of how factoring does not just apply to numbers, it applies to polynomials, right? That or expressions of this form. Or I could say x cubed is the same as x squared times x to the first. All of these is writing something on the left, just something, as a product. 8 times 6, this thing times this thing times this thing. So that's all factoring is. All right. Let's talk about some special factoring techniques. Before we get into difference of squares, let's talk about factoring out a greatest common factor, because really, what do we need to study? Do we need to study factoring numbers? No, because that's like a prerequisite for this course, right? You should know how to factor numbers. We need to talk about factoring polynomials. So let's start with factoring out greatest common factors. Okay. And let's go with example 1. Just following the text here. Part A is 3x squared minus 6x. So this is a polynomial. I haven't explicitly defined polynomial. Basically, it just means the letter x, or whatever the variable is, stuck together with numbers and other x's with different exponents. The only stipulation is the exponents have to be whole numbers, meaning you can't have negative exponents and you can't have fractional exponents. All right. So how can we factor out the greatest common factor from this thing? Well, what it means to factor out the greatest common factor, that implies that there's at least 2 terms here, and there's a 3x squared and a negative 6x. We want to figure out what is the greatest factor that we can get out of both of these terms. Okay. So what is the greatest common factor between these two? Well, I can say they both have an x and they both have a 3. They both have a 3. So I can factor out a 3x. And when I say they both have something, I mean as factors, right? So I can pull a 3x out of both of these. If I pull a 3x off of 3x squared, then I have just x left over. And if I pull a 3x off of negative 6x, the negative is clearly still there, and it's just a 2 left over because I pulled the x off and the 3 off of 6. Okay. Oh, hang on. Something's going on with, I didn't mean to do that. Sorry, 1 second. Okay. All right, so that is factoring out the greatest common factor. Now, if you want to check your answer, remember you can just use the distribution property here and distribute the 3x to both of these, and you can confirm that you would get back to that polynomial there. So let's do this one. How about 6x cubed times y cubed minus 2xy to the 4th? So the first thing I'm going to consider is the numbers. I'm just rewriting it here. Looking at the numbers, what's the greatest common factor between a 6 and a 2? It's got to be the 2, right? It's got to be the 2 because they both have a 2 as a factor. What about the x's? Well, the variables are easy here. All you have to do is pick the one that is the smallest. So in other words, if this brings 3 x's and this brings 1, then we're only as strong as the weakest link, so to say. So like we could say, since this one only has 1, the greatest common factor can only give up 1x. And similarly here, this has 3 y's and this has 4 y's to give, so we can only take 3 y's. So our greatest common factor is all of this. Now I have to think about what is left over in my first term if I take all of this away. Well, I took a 2 away from my 6, so that leaves me with a 3, right? Because 2 times 3 is 6. I took a single x away, so that's going to leave me with 2 x's, x squared. And I took the entire y cubed away, so that's it. That's all that remains of my first term there. Now my minus sign. Now I pulled a 2 off of this term, so the 2 is gone. And in fact, I pulled the x off too, so the x is gone. And in fact, I pulled 3 of the y's away, so there's only 1 y left over. There we go. All right, so that's factoring out the greatest common factor. Okay. Oh, did I miss something? Oh, I didn't write down the entire, that's fine. We did it. We did a different one. That's okay. Okay, so example 2. Now we're going to move into factoring something that looks a little different, but it's a technique that we really need to make sure we all have. We're going to factor, where is it? This thing. It's already going to be written as kind of some products, but there's a product. So if I asked you to factor just this, that wouldn't make sense because it's already factored. It's already just a product. But now I'm going to put more stuff here. Okay, so now I'm asking you to factor this thing, this whole thing. In other words, your 2 terms that you're looking at, whereas back here in example 1, the terms were like 3x squared and negative 6x. But now the terms are this entire thing and this entire thing. But what do they have in common? So I'm looking for the greatest common factor. So this one looks a little different, right? That's why it's its own example. The common term is this thing. X minus 3. Okay, so pull it out, right? That's the greatest common factor. It's like a times b minus c times b. The b is common, so we factor that out. So when we pull this out, it's going to look like, I'm not gonna rewrite it. I'm just gonna write the factored version here. X minus 3. So I'm pulling this off. Right, that is now outside, and now here comes the parentheses for the rest of what's left over, and what's left over is 2x plus 4 minus 5, which actually simplifies into 2x minus 1, right? 4 minus 5 is just negative 1. This is a very important technique that we're going to be using a lot. Let's try another one. Let me call that A, and let me give you part B here. Let's do this. 4x times x plus 2 minus 3 times x plus 2. So I'll give you a second to try it, and then I'll call on somebody to try to answer it. Okay, so we know that it's going to turn into like a product with something in parentheses and then something else in parentheses like that. So, Makira, what is the common factor here? Like last time in part A, the common factor was this x minus 3. So what's the common factor in this problem?
X plus 2.
Right, x plus 2. So that means when we factor it out, we should have an x plus 2 here. And then Maya, what would be left over right here? So we factored x plus 2 out, and what are the pieces that will be left over?
-3.
And what about the first term?
4x.
So 4x minus 3.
I said -3.
That's all right. So 4x minus 3. There we go. So this factors into this. So the point is that this thing gets pulled out and lands there, and what's left over, the two little pieces left over, are left in parentheses there. This trips up a lot of students, so I'm going to do one more thing here as an extra interpretation of part B, and this might bring it home for some of you guys. Sometimes this really helps students wrap their heads around this. Let's just temporarily name A as x plus 2. So we're just literally going to rename the x plus 2 thing as A, the letter A. Then I'm going to have this thing right here turns into 4xa minus 3a, right? Don't need parentheses if it's just, oh, whoops, I wanted to do red. If it's just a single letter. So just replacing x plus 2 with a. And now you might say, oh yeah, now I see how I can factor an a out of both of these. Stuffing that a out here, which would leave me with 4x minus 3, just factoring that a off of both of them. But then now I can just replace that a with x plus 2, and now since I'm introducing two terms, I will wrap it in parentheses now, and there we go. So that might bring it home for you. That might help to make sense of this. Okay. Is that all I want to do with factoring greatest common factor out? Yes. So now let's move on to factoring trinomials, which is a big subject, but we'll do as much as we can. So factoring trinomials. So some of this should be a reminder. All right, factoring trinomials. By the way, a trinomial is like something like ax squared plus bx plus c. In other words, it's trinomial because it has 3 terms. It has 3 terms. Okay. So there is the first method. The first method is like what I call like the classic method. The first method considers two numbers. This is going to be the one that's familiar to you. Two numbers that multiply to give the constant term. The constant term is the number at the back without an x on it. The constant term, so in the general form I've written c is the constant term here. And add to give the middle term, which if we were going to be technical, we'll call it the linear term. The linear term is the term with just a single x on it. You can say, if you like, the middle term. Okay, so in other words, I'm saying if we had x squared plus 7x plus 12, you need to figure out, the first method tells you to think of two numbers that multiply to give the constant that simultaneously will add to give 7. All right. Taylor, what do you think? What would those numbers be? Or Kimberly? Oh, go ahead, Taylor. Yep. So name like a factor pair of 12, like 2 and 6.
Yeah, I was just gonna say 2 and 6, or 3 and 4.
Right, because 2 and 6, well, it works for here, but 2 plus 6 is 8, so that's not what we want. We want that one that you said, yeah, 3 and 4. Good. Okay, so what do we do now? All right, so this is where I'm going to say what you may have learned in the past is you just kind of like, there are details happening in between, but we just kind of like ignore them, sweep them under the rug. What you may have been told is just set up your parentheses. If it's x squared here, you know both of these need to be x. We'll talk about, actually we need to talk about multiplying it out too. But, and then these two numbers, the 3 and the 4 that worked over here, they go here and here. And if they're positive, which in this case, they're both positive, you write plus signs. A lot of details happening in between that you're just kind of like, just brush them under the rug. Okay, now, of course, I'm going to show you those details in between. But first, I'd like for you to make sure that you are comfortable with going from something like this to this pretty quick, because we're going to be doing it a lot and we are not going to write the details down every time. I'm going to show you the details because, well, you should know, right? And plus it's going to tie into the stuff we were doing back here. But you need to be able to go from a nice clean trinomial like this to factored form, if it can be factored, pretty quick. But first I want to take a little detour and make sure that you know how to go from this back to this to check your answer. So let's take a quick detour to recall how to multiply x plus 3 times x plus 4. Okay, so how do we do this? You say you take the first term, x, and you multiply it by everything in here. So you act as if you're distributing the x to both of these. So I'm going to take x, and I'm going to send it to both of these. So x times x is x squared. X times positive 4 gives me positive 4x. Okay, those are my terms coming from x being distributed to both of these. And then I will send the positive 3 to both of these, giving me 3 times x is a positive 3x, and 3 times 4 is a positive 12. And now we can see how those 3 and the 4 were pretty important, right? Like with the 3 and the 4, I had to multiply to give that 12 at the back, and they ended up here pulling apart that linear term, and they need to add to give that 7 that we desired. And in fact, that is the last step here, is to combine these two middle terms to get that. Okay. Okay, so that's multiplying these back out from factored form back to standard form. All right. Now let's talk about, what do I want to do here? Oops, sorry. Before we talk about these details, let's just do some practice. What am I going to call this? Example, I'm not following the text anymore. I'm going to call it, what were we on, 3? Yeah, example 3. Let's say factor each, and I'm just going to give you probably 5 here, and we will do our best to factor all of them. I may leave a couple of them for you to try on your own. Let's say 12 is a good number to mess with. Let's say x squared minus 7x plus 12, and let's say x squared plus 5x plus 6 plus 2x minus 24. Let's just start with those first 3. And I might give you some more to try on your own, like I said. All right, I'm gonna go straight to, so we're skipping details. We're going straight to this factored form, meaning I'm going to open up all these parentheses. And in fact, I can go even further. Since all of these are just x squared, right? There's no, the understood coefficient here is just a 1. So since it's just a 1, these are just x squareds. They're not negative. No funny business happening with the first term. I can go ahead and set up the first terms in every single one of these parentheses, because I know it has to be x times x to give me that x squared. Just like back here, remember, when you multiply it out, those first two terms have to give that first, the x and x have to give the x squared. So if the coefficient on x squared is just a 1, you don't have to worry about what's attached to the x's in here because it's just going to be more 1s. Okay, so you can get pretty far without even having to think too much. Now all we need is these numbers back here and the signs on them. So it's your job now to think of two numbers that have a product of 12 that also add to give -7 in this first one. So you're thinking two numbers that have a product of 12 and such that they will add to give -7. So your negative number arithmetic needs to be on point, right? You need to recall how to add and subtract negative numbers. Or in this particular case, adding negative numbers. All right, so any ideas? If anyone has an idea, you can speak up about excuse me, what these will be.
-3 and -4.
Good. They're both negative, right? They both have to be negative. Not only do they both have to be negative so that they'll sum to give -7, but also you want their product to end up being positive. So that's good. So right here, we would say -3 and -4. And you could always multiply this all out, just like I did back here in green, to confirm that it does in fact yield this polynomial. I'm not going to check all of them. It would just take too long. That's something that you can try on your own. Now down here, I need two numbers whose product is 6 and sum is 5. Any ideas?
Three times 2.
Good, yes. So your first instinct might be to say 1 times 6, but 1 plus 6 is 7, so that can't be it, so 3 times 2. And by the way, they're both positive, no negatives happening here, so good there, they're both positive. This might be the trickiest one. We need two numbers whose product is a -24 and whose sum is 2. All right. Since the product is -24, we know that only one of these numbers that you're going to give me should be negative, right? So we are going to end up to a point where you have to tell me which one is negative. So I'm going to let you think about this, and as you come up with it, you can say something. I'll give you a little bit longer, and then I'll go ahead with the answer. Okay. It will be a 4 and a 6. But which one should be negative? Nikita, which one would be negative?
Would it be the 6?
So if we're not sure, you can say just think of the 6 as being negative. What's 4 plus -6? That would be -2, right? But we need +2, so we'll make the negative on the smaller number. If you need the sum to be positive, then the smaller number over here will be the negative one. So okay, so we've got the numbers that work, -4 and 6. Write them in, and there we go. All right. Cool. So more for you to try on your own. Let's see.
Did you say my name? Because I just got back from the bathroom.
No.
Okay, just making sure.
Yeah, thank you though. Okay. Let's see, where am I going to perfect squares? No. Here we go. All right. x squared plus 8x plus 7. So this is, what again, one for you to try on your own. And then let's do x squared plus 2x minus 15. So just write these down and try them later, over the weekend or something. And if you have trouble with them, or if you want to confirm that they're right, you can bring it up in class on Monday. So, but I'm gonna move on. And by the way, these are problems in the text. If you like, this is number 15 and number 17. So actually, the answers to the odd problems are in the back of the text. So if you factor these and want to know if you're right, you can just go check the back of the book, or just plug them into Mathway or whatever. Lots of ways to figure out if you're right about that. You can also multiply it out to check your answer. Okay. Let's talk about those details in between. Let's work with the x squared. So let's look at details in between. So considering x squared, the first one we wrote, plus 7x plus 12 is equal to x plus 3 times x plus 4. All right, here we go. Here's what we're going to do. We're going to say, if you wanted to factor this, x squared plus 7x plus 12. Oops, 12. The first thing you do is you still have to figure out the little chart thing. You have to figure out two numbers who give a product of 12 and who sum to 7. But now here comes, in this, once you get the table done in this particular kind of trinomial, you're pretty much done, right? You just fill out this the little setup here. But later we're going to deal with trinomials that are not so easy, and you're going to need to know these details in between. So this is how it goes. You say, what I'm going to do is use these special numbers to split this central term. So instead of plus 7x, I'm going to split it into two things, into a 3x and a 4x. So that's my 7x right there, splitting apart. So I'm using these numbers to split, using these numbers, the 3 and the 4, to split my middle term. And since they're both positive, right, 3 and 4, they were positive here. That's why they're positive here. Now what I do is I group the two terms. I split this polynomial, which is now 4 terms, right, into 2 groups of 2. So now I'm going to group, which literally this step, all I mean is to introduce some parentheses. Not the same parentheses that are happening here. I'm not saying that I'm writing this as a product. See, because it's not a product, it's still a sum. I'm just literally stuffing parentheses in there just for the sake of grouping them for my next step. So this does not mean I'm done. This is not a product, right? It's still a plus sign right there. And the purpose of this is now I'm going to factor out the greatest common term from here. So Kimberly, what would the greatest common factor be between these two, ignoring the 4x plus 12? Like all the way back to example 1 part A, what's the greatest common factor of these two?
The x.
Right, so we would write the x here, and I'd be left with a single x and a plus 3 inside. And then Maya, what would be the greatest common factor between a 4x and a plus 12? So if I cover this part up. Or Makira. Does anyone have an idea about, oh, go ahead, yes. So they don't share an x.
Some number, I don't know what number, but a number.
Yeah, it's just a number, right? Not an x, right? Because this doesn't have an x. Isn't 4 a factor of 12?
Yeah.
So we can pull a 4 out, and in fact, it's a positive 4, so we'll write plus 4. That plus sign just coming down. And that leaves me with an x. I tore the 4 off of that x. And the term left over, if I pull a 4 off of 12, leaves me with a 3. But now I'm right back to those problems I was describing before where you factor out a whole chunk, like the factor is this entire thing. So we pull it all the way out front, factoring that chunk of x plus 3 out, and then I'm left with the x plus 4. Okay. This is called factoring by grouping, is the name of this method. Factoring by grouping. So if you're ever trying to remember what we were doing, because we will deal with this a lot. Factoring by grouping is going to be something we use a lot. If you ever need a refresher on what the heck was going on here, it's called factoring by grouping. All right, let's try. Now, again, you wouldn't really use this method on this particular polynomial because once you have this little chart filled out, you can basically jump straight to the answer, right? So let's look at one where you do have to use factoring by grouping. And in order to do that, I need to find a problem. Oh, these are all terrible. Why can't they just give me a good problem? 5x squared minus 7x. Okay. What are we on? Example 4. There is one more step to this factoring by grouping method that I need to show you, and I'll show you it in this example. All right, so now we are running into a polynomial that does not have a leading term of 1. Or rather, a leading coefficient. Its leading coefficient is a 5, whereas the other ones were just x squared. So the first thing we're going to do is try and fill out the chart, right? That was still the first step, but what we need to do is note that when the leading coefficient is not 1, like in this case it's a 5, is not 1, we need to introduce it into our chart. The little chart we fill out with the 2 numbers that multiply and then 2 numbers that add. So if we were to fill it out like we were before, you would expect me to write a -6 here, but I'm not going to. I'm going to write a -30. Now, where the heck is that coming from? It's coming from the product of the leading coefficient, which is the 5, times the constant. So this comes from 5 times -6. And those 5 and the 6, the 5 is the leading coefficient, and the -6 is that constant term. So was that step happening back here in the last one we did? Yes, it's just that the leading coefficient is a 1, so 1 times 12 is still 12. So you never really see that step explicitly coming because of that, because it's a 1. But here, since we don't have a 1 up front, we need to consider that 5. And the way we do that is we adjust our chart slightly, a little setup here to have the leading coefficient times the constant term right there. The middle term still goes there. So can we think of 2 numbers? I'll give you guys a second to think of 2 numbers that give a product of -30 that will add to give -7. Kimberly, you got any ideas?
I'm sorry, I was still trying to figure it out.
Okay, here's one way we can try to narrow this down. Let's write some factors of 30. We could say 1 and 30, 2 and 15, 3 and 10, 5 and 6, and I believe that's it. And now we need to, now one of them is going to end up being negative. So how could I negate one of these numbers and then add them up to give a -7?
Could it be -10 plus 3?
Yes, good. -10 and, oops, -10 times 3 is -30, and -10 plus, whoops, plus 3 is -7. So our magic numbers that are going to work are -10 and 3. So now what we do, I'm going to cover this up because I need space. So I write my polynomial, 5x squared minus 7x minus 6. And what did I do with my factoring by grouping once I had the chart set up? This is when I split my middle term. My middle term using these two numbers. So I say 5x squared. Instead of minus 7x, I say minus 10x plus 3x. Okay, there's the -10 and the positive 3. And then minus 6. Of course, the minus 6 just carries over. So I'm rewriting my -7x as -10x plus 3x, which are straight from this chart. Of course, attaching the x, right? The x has to be there, but the numbers are coming straight from this chart. And then I group them, which this step is literally just slapping some parentheses around them. We do need to be careful. I need to make a note. If this term is negative, like if the 3 was negative, you want to include that negative inside the parentheses and then put a plus sign in between. We'll run an example like that. All right. And now we look at this and we go to the step where we're factoring out the greatest common factor from this, which I'm going to, just to speed things up, I'm going to go ahead and tell you is 5x. Because I can pull a 5x off of both of these, leaving me with an x minus 2. And now here, if I'm aware of what the next step should be, then I know that it must be that this should end up being exactly the same, right? If I'm going to have any luck factoring this out, then they need to be the same. So I know that this over here has to end up being an x minus 2, and now it's just a matter of figuring out what I pulled off of out of this set of parentheses. And it would be a 3. Okay, and now finally I factor this whole chunk out, x minus 2. I'll give you some time to get caught up in your thinking here. Okay, so I'm factoring x minus 2 out, and I'm left with the pieces 5x plus 3. Look at that, we factored this into that. I mean, that's an accomplishment, right? Now, before we end today, I want to talk about the little example I just mentioned about if there's shenanigans with the minus sign back here. So what I'm actually going to do is I'm going to replicate this step here, but I'm going to act as if I wrote the 3x and the -10x flipped around. So if I'm going to pick it up here just to show you what happens and what you need to be aware of. If something like this happens. So let's say I wrote it as 5x squared plus 3x minus 10x minus 6. Now this is fine. This is a legitimate, this is legitimate. It's just going to lead to something that, a little thing about the negatives that you need to be aware of. And it comes right here when we group these things in the next step, when you wrap parentheses around them. If this term is negative, when you wrap parentheses around it, you need to include that negative inside the parentheses just to avoid any kind of errors. But if you do this, you need to introduce a little plus sign there. So you're kind of, instead of saying minus 10x, you're treating it like plus -10x. Okay. And now what ends up happening is I can pull only can pull an x off of both of these, leaving me with 5x plus 3. And what can I pull off of here? Well, they're both even and they're both negative. If they're both negative, I need to pull a negative out. So I pull a -2 out, which pulling a -2 off of this 10 here will, first of all, it'll become positive and it'll also turn it into a 5. Pulling a -2 off of the -6 will turn it into a +3. And now I'm back in this territory where I've got 2 repeated terms. I'm going to pull those out. And of course, I do end up with the same answer. So the point I'm making is not that it's wrong to write it this way. It's just that in this particular step, when you group them, you need to be very aware that you need to include that negative sign in your parentheses, introduce a little plus sign out here just temporarily. And then in your next step, make sure you factor that negative out. And that negative gets factored out and then it carries all the way down, ends up right here between the x and the 2. So it becomes x minus 2. And of course, these are the same. These two are the same. They're just flipped, right? They're just in a different order. All right. Since we still have some time, let me tell you some things I want you to try to look over. Review factoring differences of squares. If you can do that over the weekend, and if I can assume you have all done that over the weekend, then we will get a little bit ahead for next time. So for instance, just a real quick example, like x squared minus 25 is x plus 5 times x minus 5. If you can review that, maybe run some problems, the examples in the text. There's literally a whole example they give for this called example 6, factoring differences of squares, in the text on page 39. All right, and by the way, you should be able to finish section 0.4 in WebAssign now because we have covered it. So if you have any issues with that, just let me know, bring it up in class. All right. I will see you guys Monday. That's all I got today.
Thank you.
Yep, thank you.